Good evening, everyone. Welcome to the Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS IISc. It is my pleasure to introduce today's speaker, Professor Frank D. Hollander. He will be speaking on the friendship paradox for social networks. Frank received his PhD in mathematical physics at the University of Leiden in 1985. From 1985 to 2024, he held positions at the universities of Delft, Utrecht, Nijmegen, Eindhoven, and Leiden. In 2024, he retired and became Emeritus Professor at Leiden University. From 2000 to 2005, Frank was Scientific Director of the European Research Institute, Eurandome, in Eindhoven, the Netherlands. From 2000 to 2007, he was the chair of a scientific program of the European Science Foundation involving 13 European countries. In 2005, he was elected to the Royal Netherlands Academy of Sciences. From 2008 to 2016, he was the chair of the Advisory Council for the Natural and Technical Sciences of the Royal Netherlands Academy of Sciences. In 2016, he was named Knight in the Order of the Dutch Lion. In 2018, he received a Humboldt Research Award from the Alexander Humboldt Foundation. Over to you, Professor.
Okay, thank you so much. So thank you very much for the invitation to speak here. It's a pleasure. I'm going to talk about the friendship paradox for social networks. Some of you will know what a friendship paradox is, others perhaps not, and I'm going to explain that to you. And the goal will be to put mathematics into this question, to this phenomenon, if you wish, and also to quantify it. And you will see what we will be trying to do. Okay.
You will not be visible.
Okay, I will stand here. Good. So I first explain what the friendship paradox is, and then I will try to quantify the friendship paradox via a notion of convergence. So we'll be talking about large social networks. And for large social networks, we're able to apply limit theorems and get interesting results. And then I will illustrate the general view that we have on this with two particular examples in which you can see everything quantified and in which there are also a number of interesting phenomena coming up. So that's how that's how the talk is put together. So, what is the friendship paradox? First of all, it is a statement that sounds paradoxical, but it is actually a fact. So it's a hard fact about networks, but when you first hear about it, it's a bit strange. So there's nothing wrong with the statement, but it smells like it is a paradox. And the statement comes from a paper in the social sciences, Gottfeld, who wrote a paper that said, on average, our friends have more friends than we do. And he came with a partly heuristic answer to that and explaining where this comes from. And this was the first time that this entered into the field. It could have entered much earlier, but nobody apparently really observed this fact. And I will have to be more precise about what this actually means mathematically. But if you first hear this, it sounds like silly. It sounds like I'm saying to you, we're all taller than our average. You say, well, that's just not possible. So how could it be that on average our friends have more friends than we do? Well, it comes in a certain way, and the precise statement will be very sharp. So I'm going to think about a social network. Here's a social network. You have people who are befriended, and these dotted lines means friendship. Friendship means they talk to each other. Every person has an opinion, and maybe this opinion travels through this network. But we're trying to go and make a statement about some property of pretty much any, well, I would say any network that you can think of. And social networks, as a mathematician, you model them as graphs. So a set of vertices and a set of links connecting these vertices. Not all vertices need to be connected by an edge. And here would be a picture of such a graph. I could also, it doesn't have to be a picture like this. This is connected. There are no loops. There are no multiple edges between two vertices. But in fact, later I will allow for even for that. So here is a very simple, this is a simple graph connected, but it could be disconnected. There could be, it could look much more complicated. We have n vertices, and we use the symbol di for the degree of vertex I. So the degree is simply how many edges are coming out of a vertex. So this vertex has degree 5. And this vertex has degree 1. Edges are undirected. Now, we're going to associate with any vertex a number, which we are going to call the friendship bias of vertex I. And I'm hanging the little n here as an extra index to sort of remind you of the fact that this is defined on a graph of size n. So there are n vertices. But forget this little n for a second. And how is this defined is in the following way. Let's first think of the case where this graph is connected. Then I don't need the brackets and I don't need this indicator. And then what this says is that the friendship bias of vertex I is a difference of two numbers. One number is the degree of vertex I, and the other number is the average of the degrees of the neighbors of I, where in the case of this particular simple graph, AI would be the adjacency matrix, saying it's if vertices I and j, aij is 0 if vertices I and j are connected by an edge, and is 0 and is 1 if they are connected by an edge, and 0 otherwise. So this would be a 0, 1 matrix in this simple picture, and you would say, look, take a vertex I, look at all the neighbors of I, which you get by summing over all the other vertices and see whether they are connected. There would be a 1 here. Count the degree of these neighbors and divide by the total number of neighbors that you have. So this number is the average degree of the vertices of the neighbors of vertex I, and I subtract from that the degree of I itself. Now, I can make it more general by saying if this would not be a multiple, if that would not be a simple graph, but a multigraph, there could be multiple edges. I say that's fine. Let aij simply denote the number of edges between two vertices A and J. So then this number could be 2 or 3 or 4, depending on how many edges there are. And I could even allow for a loop, and then I will call aii twice the number of self-loops at I. So you can dress this little simple graph up with other loops and multiple edges, and then provided you interpret this number arg properly, counting the number of edges, and you have to do a self-loop twice because a self-loop will give you a degree 2, then everything is fine, and you could even allow isolated vertices because then these vertices would have no degree, and this indicator would simply say do not look at isolated vertices because they don't have any friends, they don't have any degree, and so let's then say that their friendship bias is 0. So this is the most general formula that you can get. And the statement is, here comes the friendship paradox, take all these numbers, add them up, divide by n, which is the number of vertices. Let's call this delta of the vertex set n. And the friendship paradox says this number is always non-negative. It cannot be negative. And equality will hold if and only if all the connected components of Gn are regular, meaning that all the vertices in every connected component have the same degree. And so if the graph is connected, it means that every vertex has the same degree, and it's clear that when every vertex has the same degree, all the vertices have friendship bias 0, because everybody has the same degree. And the statement is, As soon as your network is not regular, this number is strictly positive. Okay. Now, here's a proof of this fact. And then once I'm done with the proof, I'm going to give you a little argument saying, actually, it's sort of plausible what is happening, but let's first see the proof. And the only thing that I need for the proof is this relation. If I sum aij for fixed I over all j, and I take only those j's where I connect to a vertex that is not isolated, clearly, then I get exactly the degree of vertex I. So I can count the degree of vertex I by just looking at how many edges there are to other vertices. And I'm going to use this relation in the argument that I'm going to give next. So let's begin with the proof. This quantity was 1 over n of the sum of all the friendship biases, and because there was here an indicator, I can immediately say I only need to sum over I that are not isolated vertices. The isolated vertices we carry along, but they have no friends and their friendship bias is 0. So I have this expression, and now I'm going to use this expression here to write out this di and pull out an aij. So this part stays the same, but this di I'm going to write at this sum, and therefore I can take it out and write a -1 here. And I'm going to end up with a double sum now over I and j, where I and j are such that the di and the dj are not 0. So I look at this expression, I say, well, that's not clearly, I don't see why this should be non-negative, but now comes an interesting observation. This sum is symmetric. The matrix aij is symmetric, because I'm having undirected edges, and therefore I can write this double sum as itself times 1/2 plus 1/2 the sum that I get by swapping the indices a and j, I and j, right? Because this is symmetric in I and j, and this also aij is that. So when I do that, I get 1/2 n times the same sum. The aij stays unaffected, and I take this term plus the same when I interchange I and j, right? So I have now obtained this expression, which is still not obviously positive, unless you realize that this can actually be written as a square. It's the square of a difference of 2 square roots. And once you are here, you are done with the proof, because this is clearly a sum of non-negative terms, and the only way in which this could ever become 0 is when all the degrees are the same whenever you're in a group of vertices that are connected to each other, which is where the aij are non-zero. So this proves the claim in a very simple way, and it also shows that you really can only reach 0 when component-wise you're regular, and if you're connected, that means everybody is regular, everybody has the same degree, and you would be what is called a regular graph. And for a regular graph, obviously, nobody has any non-zero friendship bias. Okay, so the proof is here, but what is really the intuition? Why is it that we have a friendship bias? Well, the reason is very simple. It is a bias phenomenon. If you are a member of this network, you are more likely to be connected to a vertex that has a high degree, right? Because it has a high degree, and so you're more likely to really be befriended with that person. So this already tells you that you will be more likely to be connected to a vertex that has a high degree, rather than to a vertex that has a low degree. And that simple fact is enough to tell you that, on average, your friends have more friends than you do. The mathematical proof is here. I don't think this intuition you see immediately from this proof, but that's an intuition way to do it. And The intuitive way would be a bit soft, and you say, well, yeah, is that what is exactly happening here? And here, this argument is very slick and very simple. Okay. Now, friendship paradox is playing an important role in a number of areas. Let me give you two examples. So, it plays a role in developing vaccination strategies when you are dealing with an epidemic. Suppose among you there is an epidemic, and I hold here one vaccine. And I want to help you, and I want to say, to whom am I going to give this vaccine, and say, please, vaccinate yourself so that you will, not contaminate the rest of the group. I don't know who is ill and who is not ill, and what I could do is close my eyes, randomly pick one of you, give you the vaccine, and say, please vaccinate yourself. That would not be a bad idea. The friendship paradox says there's a better way to do this. I close my eyes, I pick one of you, I give you the vaccine, and I say, do not vaccinate yourself. Randomly pick a neighbor, a friend of yours, give the vaccine to your friend, and ask your friend to vaccinate him or herself. When you do that, you will reach a person that on average has more friends, and therefore eliminating that person from the disease is going to do a better job. So this bias will tell you that there is a better way to spend your single vaccine rather than just giving it to a random person. And you don't need to know anything about the network, because the friendship paradox is true no matter what the network is. So on average, you're doing better like that. Okay. We all know that in psychology, we have this perception like, everybody is happier than me, and everybody makes more beautiful trips, and I only go to this silly holiday resort. This is perception, and often you think that everybody is better off than you, and in fact, that's not at all the case. So it also explains why sometimes we feel unhappy for a wrong reason. Now, for us, it will give us some information about the geometry of networks, and that's why this biasing phenomenon is interesting to analyze for us. Good. Now, it's one thing to say that something is non-negative. It's another thing to say, how big is it? So, is this average friendship bias, is it small? Is it large? Does it depend on n? In what way does it depend on the network? So can we quantify this? And the task in the remaining part of this lecture will be to go and quantify this, and we're going to quantify it for large random graphs. Large random graphs are reasonable for social networks because many social networks are indeed large, involve many people, and they are really randomly looking because they're really chaotic. How, which friendships you have among 10,000 people, it depends on all sorts of things. So it makes a large random graph is a fair way of modeling a large social network. And what we're going to do is we're going to collect all these friendship bias numbers for all the vertices and put them into an empirical distribution. So with this will become then a probability distribution on the real line, and it will keep track of the frequency of these friendship biases among my n vertices. So it's giving me much more information about all these numbers. The friendship paradox will tell you that the mean of this probability distribution is non-negative. That we have already proved. But we're going to study this object, and in fact we're going to prove under certain conditions that this probability, this empirical distribution, has a limit as n goes to infinity, and then we'll look at two examples where we can compute this limit. That's the plan that we're going to do. Now here are some papers about that have looked mathematically at the friendship paradox. There are lots of papers in the computer science and physics and social sciences literature, but almost all of them are non-mathematical, and some of them are making wonderful claims to be proved, and others are making claims that are just not true. So it's an area where you have to be careful when you do the mathematics to sort of get your fingers behind this quantification stuff here. So that's what we're going to do. Okay, how are we going to do this? We're going to take a large random graph, and if the graph is nice enough, then we will be able to prove that some convergence will happen to this empirical friendship bias distribution as n tends to infinity. So that's what we're going to do. And we're going to do this for sequences of random graphs. So because we want to pass to a limit, we now have to think of a sequence of random graphs. Well, there are a zillion ways in which you could do this, but we're going to assume that this sequence is a sparse sequence of graphs. So this means that as n tends to infinity, the degrees are not running out of hand. They stay of order 1, but can be very random. And I'm going to use Pn to denote the law of this random graph. And we're going to focus on a specific sequence of random graphs that converge in a certain sense. And this certain sense is extremely important. It's called convergence locally in probability. And basically, in simple words, this says the following. If a sequence will converge locally, if the following is true, I again close my eyes, I randomly pick a vertex, I open my eyes, and I say, what do I see around me? If what I see around a randomly drawn vertex converges in some sense, convergence locally to some sort of random law relative to where I am, then I say that my sequence of random graphs converges locally. So it is nothing other than saying what you see relative to a randomly drawn vertex converges in distribution to something. And that's a very natural notion. You have to be a bit careful about what exactly you mean by that. So I say here this has to be done in an appropriate topology, and I'm not going to spend any time on this because this is not the time to be very technical about this issue, but you have to be careful what exactly you mean by this. So what I said in words is perfectly okay, but how do you do that? And you will converge to what you see when you open your eyes, and I'm only saying is, well, you're converging locally. So you will converge to some object that is infinite around you because n has gone to infinity. And what you will converge to is a root that is from which you are looking, and the G infinity is what you see if you allow this to do for every finite distance. But this topology requires a little bit of work. Now, this is a very famous notion. It's been used a lot. And for instance, in Remco's book, this also plays a major role. For sparse graphs, this is a very important notion of convergence of random graphs. And so we bring this now to the attention. Why? Because if I have a sequence of graph that does converge locally in probability to to an infinite rooted graph, then, as a consequence, the empirical friendship distribution that I was talking about earlier will converge to a limit. And this limit is actually the law of the friendship bias of a single vertex in this rooted graph, namely the root itself. So, if you start from a locally converging sequence, you will end up concluding that for such sequences, the empirical friendship bias distribution that we had here will converge to a limit, and the limit can be described as just saying, in this limit, take the root, compute the friendship bias of this root, and the law of that friendship bias is just going to be the limit law mu. So here we have a hands-on way of really saying, not only do I converge under this condition, but I also converge to something that is represented in a simple way, and therefore is computable if you know what this limit actually is. Okay? Yeah?
Is it saying the friendship bias is a continuous function of this topology or not that?
Yeah, because the friendship bias looks at the vertex and its neighbors. And in fact, for local convergence, I can look at arbitrary finite distances, and sometimes you can peep up a little more. But so it's perfectly tuned for this. Later, we can talk about friends of friends of friends, and this will all apply. So it's the right tool, and the tool comes from graph theory, and we're happily using it here. Okay? Yeah. Good. So, as a consequence, this whole measure will converge. And in fact, even for all Borel sets, you don't have to worry about open and closed sets and stuff like that. That will all work. And therefore, we have a full characterization of this limit law in terms of just the friendship bias of a single root in this rooted random graph. And it is this step that allows us to say, yes, we can quantify the friendship paradox. It's not just something is bigger than or equal to 0. We can actually quantify the whole thing with this tool. Good. Now, in many examples, if you take a sequence of sparse graphs, you end up with a random tree. Not always. There are many examples where this is not the case, but in many examples, you will end up with a rooted random tree. Now, for a rooted random tree, everything becomes even more simple, because here would be the root, here would be some random tree, and then what is the friendship bias of this root? Well, you just have to count the number of neighbors, the degree of the root. You have to count the degree of the neighbors of the root, and then you can make up this number. And if you know what the random tree looks like, you can compute the law of this random number, and you don't even have to think about anything more complicated, and you get your hands on this very, very quickly. But not all sequences of locally convergent graph converge to trees. There could be triangles or other things around, but there are many that do. Certainly interesting ones. Okay, so we have a hands-on approach to compute this distribution, and that's what we're going to do, and we'll see that there are some interesting questions popping up when you try and compute the law of this object, which would then be the mu that we desire, which is the limit of the friendship bias empirical distribution that we started out with at the beginning. So, now before I say something about examples, I want to point out one thing. We already know that this measure is non-negative. It's the limit of an empirical distribution, of which we know for every n that it had a non-negative mean. That was the friendship paradox in the first place. So certainly this is always the case. We can ask, well, the mean is non-negative. What about the median? Is the median also non-negative? And if the median is also non-negative, that means that the half-line gets more, at least half of the mass, then we say that the friendship paradox is significant. It's just a name. You could call it poodly-poo. It doesn't matter, and non-poodly-poo, but we called it significant and insignificant. And if the median is negative, then we would call it insignificant. Why? We would say, look, the mean is positive, but more than half of the mass is on the left of 0. They would say, well, that's a bit strange. So, well, it's not strange, it can happen, and we think that if you're in the significant case, then you're saying you're really, this friendship paradox is really true in a very significant way. At least half of the vertices have a positive friendship paradox, friendship bias. So this is a notion that we introduced, and it will come back in the slides that I talk about later. There are many other things that you could have done, but we chose to look at this also as part of our quantification. Okay, 2 examples. So now we get to that. And in the paper that we did on this, we have a whole range of examples that we look at and try to quantify what does this limit mu look like. Is it significant or is it not significant? What can happen? How does it depend on all sorts of parameters from in your model, and et cetera, et cetera. And this turns out to be an interesting, looking around for what might happen. And Remco's book has hundreds of examples, let's say at least 50 really nice models that you can pick out and that are very well-known examples of random graphs. And we picked a number of them, and I'm only going to focus now on the 2 easiest examples for you to see how, for these examples, all the formulas that I said before are actually going to work out. What are they going to produce? So can I find what this local weak limit is, and can I compute the law of the friendship bias of this rooted graph that arises as the limit? Let's see what happens. Okay, so the most simple model is the Erdős-Rényi random graph. You pick a parameter lambda, positive and finite, and you pick an n. And the Erdős-Rényi random graph is what you get when you put all these vertices on a circle, and you decide for every pair independently to draw an edge there with probability lambda over n, and no edge with probability 1 minus lambda over n. A little fact is, if to be able to do this for every lambda and abd n, you should cut the probability from above by 1, but we're going to be interested in letting n tending to infinity and keeping lambda fixed. So this for large n you can drop, and it's useless. So this is a graph where you say I start with the complete graph, and I'm basically diluting the number of edges by saying I'm only going to keep you with the probability lambda over n. And the choice for lambda n is very crucial, because lambda is the average degree of a vertex in this graph when n is very large. Why? Because every vertex has n minus 1 possible neighbors. Every neighbor has a probability lambda over n to be connected to that vertex. So the average number of neighbors of a vertex is lambda times n minus 1 over n, and that's converging to 1, to lambda. So lambda gives you the average degree in this Erdős-Rényi random graph. Okay, for this Erdős-Rényi random graph, there's a very basic fact. As n tends to infinity, this sequence of Erdős-Rényi random graphs for lambda fixed and n tending to infinity does converge locally to a rooted random tree, and the rooted random tree is very simple in this case. It's just a Galton-Watson process starting from one vertex, which is the root, and every individual in this process has a Poisson lambda offspring distribution. So the distribution of the number of offspring is random and follows the Poisson law with parameter lambda. So, yes, for this example, there is a limit. And we know what the limit is, and it's very simple. So, let's compute then some properties using this description of our limit. So, we are now, what we have to do, delta phi is the law. So now that is that's a random variable, and it is the friendship bias of the root in such a Galton-Watson tree. And here's a number of facts. If lambda goes to 0, so then the edges are very rare. The friendship bias is going to, on average, go to 0, and even its variance is going to go to 0. But if you make lambda very large, the friendship bias will converge to 1, and its variance will converge to infinity. So a completely different kind of behavior for large and small densities. You can prove that the probability that this friendship bias is large for a large x sort of decays super exponentially fast with all sorts of detailed prefactors that you could put in front of here, and this has something to do with the Poisson distribution, but it's not just the tail of the Poisson distribution, because the friendship bias is different from the degree. It looks at differences of degrees. So here you have a very fine description of how unlikely it is to find a vertex that has a very high friendship bias. Here is a theorem that focuses on the significance. So what is the probability that a vertex has a non-negative friendship bias? Well, out of this Poisson tree description, you can write down what a formula for that is. And if you plot this formula, it starts for lambda small at 1, and it goes down monotonically to 2.5. So this is a picture of this function as a function of lambda. We can prove that the limit here is 1 and the limit there is 0.5 on the other side. And this picture is there, and we cannot prove that this quantity has this picture. If you look at this for the first time, you would say, give me 2 hours on a Sunday afternoon and I'll prove this for you. And I can reassure you that even the weekend afterwards, you haven't figured this out. It turns out to be really tricky. And here you can still do a lot. Here it gets very difficult, and you would need very fine estimates to do that. And Evgeny Verbitsky and Rajat Hazra have now done this with some sort of computer-assisted proof. I mean, there's no doubt about it, but it's hard to prove. Fun, nothing more than that. I also plotted here the fraction of strictly positive vertices and strictly negative vertices, and they are plotted for the Erdős-Rényi graph like that. And you see, at least numerically, that the red ones are always more than the blue ones. So it is always the case that for any lambda, you have more vertices with positive bias than with negative bias. I already know that on average everything is positive, but this is a stronger statement. And there's a little kink here, I don't know why. So something is happening, and you would say, isn't this around lambda is 1? No, it's not around lambda 1. It doesn't have to do with that. So, indeed, there is a strong form of significance that the positive ones are really always more numerous than the negative ones. Okay, I have a bit more time to go, so this is the second and last model of which I want to show what this friendship bias is doing. And this is the configuration model. The configuration model is a model where you uniformly at random draw a graph with a prescribed degree sequence. For me, the vertices have a label. You could say, well, do you want to reshuffle them? No, I don't want to reshuffle them. They have a number, okay? And what you do, you say, I would like to have a graph consisting of 6 vertices, and these 6 vertices are supposed to have degree 1, 3, 1, 3, 2, 4. Okay, this you choose, you get to choose this, and I say I'm going to give you a very simple algorithm, and some of you will have heard this. Put the vertices 1, 2, 3, 4, 5 on a ring. Put half edges down, 1 half edge, 3 half edge, 1 half edge, 3, 2, 4. This picture is deterministic because you have chosen this sequence, and once you've chosen it, this is the picture that represents your choice. And now I say randomly pair up half edges to turn them into an edge. So these two, for instance, could have teamed up and produced this edge here. There could be 2 here and 2 here that could have matched up, and that would have given a multiple, a twofold edge. And when you're done, you get a random picture because you are randomly matching, and this is a random choice from such a sequence. Now, this is a very basic thing and a very basic and simple algorithm to generate a graph that has a prescribed degree sequence. So, can we, for this graph, also do an analysis of the type that we do? And the answer is yes. The very first thing that we need to check is, does this graph converge locally to a limiting graph? It does, provided you assume a few properties of the way you chose your degree sequence, because you got to choose the n in all the degrees, and I say you have to do that in a reasonable way in order to get some sort of limit. And if dn is the degree of a uniformly chosen vertex, so it means with probability 1, 6, you pick one of these 6 numbers, and that will be your random degree. If that random degree converges in distribution to a limiting random degree, and it also converges in mean, and the limiting degree has a finite mean and is positive with probability 1, so that I'm kicking out isolated vertices, then I'm going to converge again to a random tree. This random tree is again going to be a Galton-Watson process, with the sole difference that the root has a slightly different offspring distribution than all the other vertices. So the root has, as an offspring distribution, the distribution of this limiting random variable d, and all the others have the same thing, except you bias the degree in this way, and therefore this is a biased, linearly biased distribution. And the statement is, in the configuration model, under this assumption, you will converge locally to a random tree, and the root is just slightly different than all the other vertices, but the offspring distribution of both is completely given in terms of these 2 probability distributions where k is running over the positive integers. There's one particular case of interest that is fun to look at, is that if this distribution here would turn out to be a perfect power law, and we call this the zeta offspring distribution, and it can work for any tau strictly larger than 2, because I need this mean to be finite. Now, here are some theorems. For general offspring distribution, the mean of the friendship bias is the quotient of the variance of the degree distribution divided by its mean. So you see that this friendship bias does have something to do with means, but it's not literally the same as the mean because it's talking about difference of degrees. If the second moment is finite, then you can also compute higher orders. And in particular, you will see that the variance of the friendship bias is always bigger than or equal than the variance of the degrees. And that is also reasonable because you are starting to randomly look around you and you are more volatile in your friendship bias than you are in your degrees. For the zeta offspring distribution, it turns out that the friendship bias of the root has a polynomial tail, and the tail is shifted by 1, so you don't get here x to the tau minus 1, but you get tau minus 2. So this comes from the fact that your friendship biases tend to be bigger than your degrees. So here you have a polynomial tail, which is very different from what we saw for the Erdős-Rényi random graph, where there were Poisson offspring distributions and you had a super exponentially small tail. If I plot again whether this process is significant for the zeta offspring distribution, it's always significant, and there is a very narrow window in which we could do the numerics and show that this fraction is not just larger than a half, it's actually very big. It's never more than 1, of course, but here the lowest peak that it will ever reach in our simulations is something like 0.84. So for the zeta offspring distribution, there is really most vertices, the majority of the vertices has a positive bias. So it's like 85%, and the moment your tau plays up, you will see that almost all, if tau gets a bit larger, almost everybody has a positive friendship bias. And here again, I could say, yeah, could you also be more precise and say, what is the fraction of negative vertices and positive vertices? And again, we have done that with red and blue curves. These curves are not sharp because the formulas that you get are long sums, and we put in what are the errors of our numerical simulation. But you see again that the red vertices are always winning over the blue vertices. So also in this case, you always have more vertices with a positive friendship bias than vertices with a negative friendship bias. So again, there's a strong form of significance also in this model. And now there's much more to say about this story. There are lots of things that we have done afterwards. We looked at friends of friends and how does this all work. We looked at CLTs, large deviation principles, other things than degrees. But let me stop here and say that was the story about the simplest version of the friendship paradox and how can you quantify it and what does it give in just 2 particular examples. Thank you very much.
Thank you, Frank, for accepting our request and delivering an interesting talk. We have 6 minutes for any questions because we have back-to-back talks and we'll break for 15 minutes from 5 to 5:15. So over to the audience.
So I have 2 questions. One is that you mentioned the sufficient condition for mu n to converge to mu, that gn should converge to g locally.
Yeah.
So what do we know the necessary conditions like for mu n converge to mu, or this is the only condition that we have till now?
No, I think this is not a necessary condition, but my feeling is that it should also not be too far from a necessary condition. Probably because in the end the quantity that you're interested in is the friendship bias of the root. It could be that for some reason, even though you have different environments of the root, they just happen to give you the same value of the friendship bias. And so I don't think it's an if and only if condition, but I would sort of say if you're happy to accept that by and large, this should be the right thing to do.
So another is that you gave a inequality of the tail probability, like probability of
Yeah.
delta phi greater than x is less than, yeah. So here x is going to infinity, like
Yeah.
is it also meaningful to ask like concentration inequalities in this case, or does kind of that
You
are
could,
there
but it's not
existing
going to concentrate. I mean, okay, so for very small lambda, you see that everything goes to 0 because that has to do with the fact that everybody gets disconnected and there are very few edges. But here, things are getting big in mean and in variance, and this number is not going to concentrate on something. I don't think there is a law of large numbers for this. And so it has a non-trivial distribution of which this shows, it just gives you some information about the tail of that distribution and nothing more.
Okay, yeah. Thank you.
Okay.
So, was this verified like empirically with a certain group of individuals or anything?
No, not these fine details.
Not like
No,
generally.
because of course the friendship bias paradox has been seen in many examples numerically, and that's also how it was sort of discovered. But these are very detailed, mathematical, sharp results, and I haven't tested them against real networks because, of course, here an important point is also that I'm putting myself in a limit when when n goes to infinity. If you not do that, you cannot get very sharp results. It would be interesting to see whether you could get a CLT or something, and then you could start to have some estimates about what would be happening for large but finite. And I haven't done that, and I don't think in the mathematics literature there's anything like that yet. There are very few papers on the topic that are mathematical.
because for empirical, how would you define friendship in the starting case? Like, how would you tell two people are friends and then take it as a problem?
No, I mean, in your original graph, it's very clearly defined. You have a graph. I give you all the degrees. I read them off. I can build up all these numbers for every vertex, and I can put them into an empirical distribution. So the moment you give me a graph, no matter what it is, I get an object here. That is a deterministic function of your graph. And all I'm saying is that if this graph is chosen in a random way, in a reasonable random way, this probability distribution is going to converge to an interesting limit that I can compute.
Got it.
Okay, so that's the train of thought.
Thank you.
Professor, that empirical tail distribution you have shown,
Yeah?
can we validate to build on his question? In real network, can we find some empirical extreme value distribution and see if it matches this trend? And
Yeah, I guess if you would start with a network that would be large and that would be Aders-Rainy random like, you should find a law. I think the law, the problem is the law is not simple. It's not something you say, okay, that's just Mittag-Leffler's law here. No, all these laws are complicated functions of the graph, and if the graph is random, they will give random distributions. But certainly you could pick a random graph, take 10,000 realizations of it, and see what the distribution of this random variable was. You can plot, and for instance, in these pictures, I've plotted this one number, which is the significance, so it's telling me something about the median of the graph. So this you can do, and this whole distribution you could also plot. But to see tails like that, you would have to be very precise.
thank you, sir.
But it's doable.
I have one question. So the intuition that you said in the beginning was that nodes would attach to high degree nodes, but that's more of a preferential attachment than the random graphs one, right?
No, it's not a preferential, but it has to do with there's no preferential attachment, Laurie, I could ask the question about a graph that was generated according to a preferential attachment model that we could do. This is just a phenomenon that you say, if you start to look at biases, like how many friends do my friends have and you, then it's a simple fact that if I randomly pick a vertex, that this vertex is more likely to be connected to a vertex that has a high degree, and that's why it is more likely to have a friend that has a high degree. And that is just a simple fact, has nothing to do with preferential attachment or whatever. And the friendship paradox is true for every deterministic graph that you can choose. There is no graph in the whole world for which this fails. So it has nothing to do with the law of the graph. It's interesting, we also did that to look at the friendship bias on a preferential attachment random graph. It becomes more complicated, but because its local limit is a Podia tree, and it's not a Galton-Watson tree, but you can do things, and you can do similar things like here. But that's just, you choose your graph model, but the first part of the theory is completely general.
Thank you.
In both the examples, the bias was significant.
Yeah.
It's just that the heavy tail makes it strongly significant. Is that right?
Yeah, in both cases, it turns out that it's significant. In fact, it's hard to beat significance. We've been able to come up with some very strange graphs for which it would not be significant, but by and large, if you just pick your favorite random graph sequence, you will predominantly find that significance holds. And in particular, for some graphs, for instance, for trees, finite trees, we can prove that every finite tree is such that there are more vertices with a positive degree than finite negative degree, and that's a hard pointwise statement. So by and large, you will see that significance dominates, but it's not true for any law of random graphs.
So maybe I'll rephrase the question that was asked to see if it makes sense. So given an arbitrary, very large graph, say empirical, say observation, we sample various nodes from the graph and we compute this friendship bias. And then we look at the kind of the tail of that to see if it kind of matches this, to see.
Yeah, that's what you should do. So if you want to see this, you generate many times an Erdős-Rényi random graph or a larger one, and you random click a point and you start to look at what you see. And if you ask when is this, what is the tail of this distribution, you will find this.
I'm saying if we want to see whether the given graph is kind of close to an Erdős-Rényi.
Okay.
So that is a kind of test of hypothesis.
Again, the friendship bias of the root is not a unique function of the graph below it. You could have two local pieces of the graph that happen to produce the same friendship bias. So there's a projection going on from the whole graph to the friendship distribution. This comes from this formula here, that you say, okay, you have a random graph, now you should look at these numbers, and then you have to compute something. So you can all do that, and I think if probably you will see, if you see something that looks like the tail of an Erdős-Rényi random graph, you could say, well, probably it is the Erdős-Rényi random graph, but you cannot, it's not an if and only if condition, because the degrees, the friendship bias is a projection, some sort of projection of the degrees. And so you wouldn't be able to invert it.
About exactly the same question that, but if you have to do it for Erdős-Rényi, there has to be a moderate deviations type. How fast can X go with N, right? In your, so you have taken N going to infinity, and then this is there, to compare to a L1, you would need.
Oh yes, this would be possible. You could start to worry about how close is your mu n to your mu. We haven't actually done that. Because there are many questions you can answer, and that is something that you could do. I mean, so you can talk about errors and how fast is, how good is your convergence at the level of graphs, and what would that imply for the rate of convergence from UN? It's these are all interesting questions, and I haven't seen them done in the math literature.
Any more questions? May I suggest that can we take it during the break? Yeah, we are already 5 minutes over.
Okay.
So thank you, Professor,
Thank you.
for the talk and the audience for the questions. We'll now break, and we have snacks arranged in the coffee hut. Please help yourselves. We will be back by 5:20 p.m.